Hello, it's time for a new topic. And next up, we've got thermodynamics. So, this is looking at energy and heat, and it's going to fill a gap that we've got in our description of energy that we've created so far. So, let's quickly recap where we are with energy. We started in classical mechanics, and that's looking at macroscopic objects, and we could describe the energy of these macroscopic objects with their energy of motion, which was the kinetic energy, and energy of position, where really we were looking at gravitational potential energy and elastic potential energy, once you brought in the materials part of all of this. So we had quite a nice, straightforward description of energy that was easy to calculate because mostly we were dealing with one object at a time, maybe a couple of them, but it wasn't anything particularly difficult to do. So that was where we were with these sort of real world sized objects. Then we moved into our subatomic scale of objects, and we were looking at atomic nuclei. So we had our atoms, we were looking inside the nucleus of atoms, and we were seeing the arrangement of these nucleons, these protons and neutrons, and we were looking at the binding energy and how different binding energies of different atomic nuclei meant that we could get an energy release in our nuclear reactions. So that's what we were doing there. We've got this gap in between though, because obviously to move from an atomic nucleus, we have to go up to an atom, and then we can combine all of these atoms together to create molecules, and we can combine the molecules together in order to create solids, liquids, gases, to make these bigger substances. So we've got this in between ground. We've got the microscopic, which is sitting between the macroscopic and the subatomic, and we haven't said anything about the microscopic and the energy that's going on there, because clearly we've got more things happening. When we were looking at the subatomic stuff, we were considering how the binding energy in the nucleus. Well, now we've got atoms bound together, so we've got another system of objects arranged in a certain way, which is going to bring us more potential energy. We need to describe this potential energy. This is going to be essentially another type of binding energy that we've got here. So we need to say something about that. We've also got the motion of these atoms and molecules, because when we were working out the kinetic energy of a macroscopic object, we were just thinking about, well, here's the center of mass, essentially, of the macroscopic object. How is that center of mass moving around? And we'll just consider that in our half mv squared to just be this thing, this little bit of stuff, whatever that ever meant. We were just ignoring all of the internal complexity of it. We weren't thinking, oh yeah, this block is made up of atoms, and each one of those atoms is vibrating backwards and forwards inside its position its position inside the structure of this object. So we weren't doing any of that. We didn't care about that. But all of these atoms and molecules are going to be moving around. So we've got more kinetic energy there, which we haven't considered at the macroscopic or the subatomic level. So this is a whole new load of potential energy and kinetic energy. And this is what we're calling the internal energy of a substance. So we need a description of this internal energy, and that's what we're doing in thermodynamics. And it has its challenges, but at least that we know what our aim is. How are we going to describe all of this? And this is going to be related to, is bringing in all stuff to do with heat, because that's going to be how the energy is moving around. Temperature, it's a different way of describing the energy inside these substances. So this is the language we're moving into now. Heat and temperature are all the language of thermodynamics, which is all looking at microscopic energy, the energy of microscopic particles. Right. So how are we going to navigate our way through all of this? The first major challenge we've got to all of this is, how do you describe the behavior of systems of huge numbers of particles? So by particles, I mean in atoms and or molecules. So particles is just the catch-all term for that. You know, in classical mechanics, as I say, we were only looking really at one or two objects at a time. In nuclear physics, we might be looking at a couple of hundred nucleons. So if we were looking at some uranium, we might have, what is it, uranium 235, 238 or whatever. So we've got 235, 238 nucleons there. That's quite a lot of them, but we were averaging things out by talking about binding energy per nucleon. We had a way of handling this order of magnitude increase in the number of particles that we were looking at. Now we're going to things like gases, which we'll certainly get onto in this topic. The number of particles is just incomprehensible, really, and it's so large. How on earth do you manage that number of particles? And here we get another split between classical and modern physics. We've got two ways of thinking about this. We've got classical thermodynamics and we've got statistical mechanics. Right, so in classical thermodynamics, we're using the measurable macroscopic properties of matter. So we will talk in terms of, well, mass, volume, pressure, what else we've got, temperature, things like this. So these are all things that we can measure for a large volume. You know, we can get a balloon full of gas and we can measure all of these things. We can get the mass of this, we can get the volume of the balloon, we can get the pressure on the balloon, and we can calculate, we can measure the temperature. None of these things require us to have a detailed description of every single particle inside the balloon. So that's option number one. And that is the option that we're going to take, surprise, surprise, because this is in our classical physics. And as we said right at the beginning, pretty much everything you do when you start learning physics is classical physics. So we're going to be looking at classical thermodynamics. The other option that you've got is statistical mechanics. So the two words here pretty much say everything about it. You've got statistical, as in we're using statistics to describe the behavior of an enormous number of particles. So you'll be looking at distributions of saying, you'll have various curves, which will be saying things like, this is the distribution of energy or velocity or whatever it might be of particles inside a gas. Here's our distribution. So we can now apply statistical methods to all of these particles in order to describe the behavior of what's going on in the gas. So you're not looking at individual particles per se, but you are describing them all in the context of a distribution. And the mechanics part, well, we've already dealt with mechanics before. This is talking about how things are moving around. So we're using statistics to describe the motion of particles in a gas. So it's all distribution based, probability based. And then you can say, what's the probability of a particle having a certain energy, having a certain velocity, this sort of thing. That is more complicated than we are able to cope with in pre-university physics, mainly because we don't know how to do statistics that well. So, we don't really do all that much in statistics before we go off to university. So this is way beyond what we're going to be able to do at the moment. But it's worth having in mind that this is the modern physics approach to thermodynamics, that it really is built around statistics and statistical mechanics. Right, so having said that then, and that we are going to be looking at classical thermodynamics, what is our path going to be? Well, we need to start off unpicking the different phases of matter. So by phases of matter, I mean solid, liquid, gas. We're not going to be dealing, at least in detail, with the more exotic phases of matter, things like plasma or the Bose-Einstein condensates and things like that. So we're not going to be dealing with those. We're going to be looking at what is distinguishing a solid from a liquid to a gas, because clearly there is an energy factor going on in all of this. The more energy that you're putting in, you heat up a solid there. So you put some energy into a solid, it becomes a liquid. You heat up the liquid, it goes to a gas. So we've got changes in internal energy here. So we need to think about the internal energy and how it compares for solid, liquids and gases, because we're trying to describe the energy in these substances. Then we need to look at what are these macroscopic properties of thermodynamics. If classical thermodynamics is all about using macroscopic properties of substances, we need to know exactly what these things mean. What is temperature? That's not an easy thing to answer if you haven't thought about it before. Similarly with pressure. And we're mostly going to be looking at these in terms of gases. I mean, you'll see that I've got down here ideal gases. I mean, this isn't necessarily the exact order that we're going to do everything because it's interrelated. But in gases, it's a bit easier to describe things because you can start ignoring the potential energy, or at least assume that there is no potential energy. Just start looking at the kinetic energy. Then we can start looking at how things like volume, pressure, and temperature are related macroscopically, and then start building in a microscopic underpinning of this, of thinking, well, where is this actually coming from? What is the temperature on a microscopic level? What is the foundation of this that we're describing at a macroscopic level? The same for pressure. Where is the pressure? What's causing it? Where's it coming from? So we start getting that link then between the macroscopic and the microscopic, and we're going to be doing that by looking at gases. There are a few other things as well that is going to be worth unpicking. I mean, entropy is a big one. It's a complicated, or at least a hard to grasp initially idea. It takes a bit of getting used to, this measure of the order of a system, or the energy that is available for doing work that's in a particular system, and then how that will evolve over time. So essentially we're looking at the idea that if you've got a concentration of energy in one area, it will tend to spread out in some way. So entropy is talking about the movement of energy really, and the order within a system. So because we know that the movement of energy we can describe in terms of work. So if you've got a concentration of energy and that energy is going to spread out, then it's doing work. So we can think of entropy in that way, and it gives us another way of describing how energy is operating, how it behaves, and how it behaves over time. So that's why entropy is so important. That leads into the laws of thermodynamics. There are 4 laws of thermodynamics, some of which, well, they're all quite difficult to grasp the nuances of, which is why they don't get covered that much before you head off to university. So we'll try picking away at those just to see a little bit more of the depth involved in them. But the nuances are quite complicated. So, but they are going to be covering things such as why we can set up a temperature scale, how systems evolve over time in terms of entropy, the conservation of energy, the existence of lowest temperature, a minimum energy in a substance. So all of those things are consequences of the laws of thermodynamics. So we'll say a little bit about those. I mean, there's only so much detail we're going to be able to get into. And then, of course, we've got a lot of stuff with calculations. We always have things with calculations. It's nice to be able to quantify things and describe things in a more precise fashion. So we're going to have calculations at a macroscopic level where we're looking at specific heat capacity. So how much energy needs to be supplied to a particular substance in order to get a certain temperature change. So we're going to be looking at that. We're going to be looking at also macroscopic mathematical descriptions of gases in terms of temperature and pressure and volume. And we'll also start looking at that and at the microscopic level as well, and describing the kinetic energy of particular particles in the gas. So there's still a lot of calculations that we can do in all of this. So yeah, there's a wide range of stuff to cover. It's conceptually can be quite difficult in parts, particularly if you really get down into the weeds. So we've got to try and cut our cloth in the right way here, of not overstretching ourselves, because that's quite easily done in thermodynamics, and you can get stuck into the weeds of evolution of different systems and how their entropy is changing, and it gets complicated very quickly. But hopefully we'll be able to walk a sensible path that will just take you beyond the sort of stuff that you'll be typically doing in your standard A-level syllabus, and giving a bit more depth and context to all of that.